Right, welcome everybody. Again, today's session is on data review. So we're in day 3 of our 4-part series on kind of the basics of statistics within ARM. The first day we did an overall presentation of statistics as it pertains to ARM software. Last time then we did data confirmation, really the tools to use when you're putting the data into the program to make sure that the data is correct and accurate and catching any outliers. Today, now we're kind of taking the next step. Now that the data is in there, let's prepare it for analysis and really looking at the assumptions of AOV. So I'm going to close this presentation and just real briefly recap some of the slides from that day 1 that pertains to today. And so we had talked about, we kind of stepped through all the analysis that's done with the data, but we said all of that, that analysis of variance is really great, really powerful, but there is a gotcha there in that there's some assumptions that analysis has. We're assuming that the data has certain qualities to it in order to do that analysis. And so we had talked at length, we'll go real quick here today, that there's four main assumptions: homogeneity of variance, that the data is normally distributed, and then independence of errors and additivity. We really don't test for, but those first two are the main ones that we'll focus on today. That there are tools to help visualize, but maybe even more efficiently, we can run statistical tests. That'll give us a confidence, I guess we could say, not a for sure thing, but a confidence to the fact that our data is meeting those assumptions or is not. And along with those tests, then, if we find out that particular data doesn't quite fit those assumptions, then we have a toolbox, if you will, of things we can utilize in order to either adjust the data, which would be kind of the data correction transformations, which really keeps the results the same, but transforms the data points so that way the distribution does fit our assumptions, so we can trust that analysis when we get to it. Or there's some other options. We kind of pivot away from the AOV and say, well, let's run a non-parametric test instead, or maybe turn to a spatial model. We probably won't spend a ton of time on those spatial models, but we'll kind of show in ARM where we get to those, but we'll spend most of our time on those other two options. So with that, we can dive in here to ARM. And so I have a trial open here. Got a variety of assessments. The specifics of them probably don't matter a whole lot, but just have a few different assessments that we can step through and kind of look at how to go about reviewing the data. And really, pretty much all of the features lie on one panel that we'll utilize called column diagnostics. So over here on the right of the assessment data editor, you may have the properties panel visible, or maybe not. If you do have it visible, you can unpin to make that hidden again. And that goes over to the right here. That properties is shrunk down. And so we also have a couple of other panels here. And the one I'm interested in is column diagnostics. So I'm going to click on that and then press the pin, so that way it'll actually stay visible for us. And it's a little wider than some of the other panels. So I'm going to just drag this out a little bit so we can see a little more. Trying to find a sweet spot here with these panels and the information to display. So this panel here at the top, we can see it says column 1 diagnostic. So it's going to refresh depending on which assessment column that I'm clicked into. If I click over here with 2, you can see it refreshes and changes its calculations based on the assessment that we put our cursor into. So there's a couple of sections here on the column Diagnostics. The first one is called Diagnostics here. And so there is a table of information for us about this assessment. Quite a few different pieces of information. These first few rows maybe fit a little closer to the data confirmation step, just giving us information about this assessment. So there is 24 individual values that we have in this assessment. 11 of them are unique. So there's a few of them here. I can see right off the top, 2 of them are 71. So we can just see how many different unique values are in the column. If any of them are being thrown out for a variety of reasons, that analyzed would tell us so. Looks like they're all being included. And these would be the different ways that they might not be included in the analysis, whether there's a missing data point, I just left it empty on purpose or by accident, or if it's damaged. So you can kind of give those a glance, again, kind of more data confirmation level on some of that information. For our data review, we're a little more interested in these rows down here. Right after the treatments, we have Levine's, Shapiro-Wilk, skewness, and kurtosis. And if you recall, those were the tests, statistical tests that we had talked about in those slides as being the tests for those assumptions of ANOVA. So here on this dialog, we are running those statistical tests on this data column and reporting the results. We have 2 different columns here of results. The raw column is simply looking at the raw data and calculating the tests. However, we're a little more interested in the second column, IID. This is referring to the residuals. So one of the, I guess, changes relative to some of the older data review features that ARM had offered previously is that a little more modern statistical approach is to actually run these statistical tests on the residuals of the data instead of just the raw data points. The idea being the residuals kind of are really basically the error behind the scenes in a sense. And so we really are wanting to test whether those errors are homogeneous invariants, whether they're normally distributed. And so that's really our focus here on this tool then is the results of these 4 tests on the residuals here. And so what we see in this table are p-values. So this would be the Levine's test, testing whether there is homogeneity of variance or not. And we have a very large p-value. And so that would tell us that we have very little confidence in rejecting our hypothesis for the Levine's. In that we don't have any problem then with the test. So a long story short on here, we're really looking for, or we're hoping not to see significance essentially in these tests. And none of these values are significant. They're all well above that 5% level that typically is looked at. So we can conclude we really don't have any problem with the assumptions in this column, which is great. We don't really have to reach into our tool bag and do much with that. If you don't want to have to dig into these numbers, maybe it's a little much or wanting to go a little faster, we do have a second panel here called recommendations. And that actually summarizes those 4 tests that we had up here, brings them down here, and ARM looks at each one of them, and based on the results of that test, here in our case, Levine's was not significant, then ARM gives us a recommendation of an action to take. Or in this case, it's kind of no action to take. It's this IID action code. And so in this case, the IID action code actually isn't going to change anything in the data. It isn't a data transformation, but it's a nice kind of clever way to mark this column as reviewed. So, if we didn't take any action and we just move to the next column, then there's really nowhere in that column where we're marking that we've actually looked at that column. So somebody else, or if we come back later and don't really remember, we could look at that and not be sure if we actually took a look or not. So if I double click into this row here, or I could click the IID check mark up above, either one of those will do the same thing. It will apply that recommendation into our column. In this case, it just puts that IID, which really says ARM isn't going to do anything to our data in the analysis, but we kind of marked it that we have actually reviewed the column. And this is just an action code. If I display the list here, there's just one of the many action codes we have. And it basically is just instructions for ARM to analyze the data, just like normal, no special action that needs to occur. So this one was easy, not a lot we had to do. If we click into column 2, now we'll see again that the whole screen is updated now with the analysis for this column. So if we come back to the diagnostics, if you're kind of a numbers person, we can come back here and look at those 4 numbers here. Oops, I did not mean to click on that. We'll stick back with the raw data for now. We can see that there's some highlighting here. So the Levine's is highlighted, and we can see that that test is actually significant. It is less than our 5% cutoff value. So that tells us that there actually is something that we need to deal with. The Levine's is failing, so we don't currently meet that assumption of AOV that the variances are homogeneous. We could bring up a box whisker graph where we wanted and take a look at it like we had done last week if we wanted to kind of visualize that, but it's telling us that there's a fair amount of confidence. We're 98% confident that there's an issue with the homogeneity of variance. So we say, all right, well, that's a problem. We can't just mark this as IID and move on. What should we do? And that's where the recommendation section really shines. ARM will look at the data and decide for us what would be a good action to take that can resolve this issue. And so you'll notice that there was additional columns over here, AL, AS, and AR. These are a few different data transformations that can be done, specifically the log transformation, the square root transformation, and we'll deal with AR a little later. But essentially, we can see under AL that the Levine's value for AL actually is not significant. So if we were to apply the log transformation to this column, then the Levine's will not fail. Then the distribution of that transformed data now has homogeneous variance, and we can trust our analysis then if we do that. And therefore, we have the AL action code down here as a recommended action because it will stabilize the variance. Now, one thing to note, within this recommendations panel, we can train ARM to know maybe even more and make an even better recommendation for us by changing this basis. So right now I have it set to assessment values. So ARM is just playing a numbers game. It's just looking at the numbers in this column and deciding, checking those different tests and deciding, which one would fix it. But we can have ARM consider the information in the action codes or the information in our rating type or the rating unit to have ARM know what type of assessment is this. So in this case, this is count data. So if I change the basis to rating type, my recommendation changes because ARM knows that count data typically pairs well with the square root transformation. So you'll notice that this table changed and we took out the log transformation because the log transform isn't typically used with count data. So instead, we kind of eliminated that option and we said, all right, this is count data because ARM now has been told that that's the type of assessment that this is. Well, if it's count data, I know a square root is better. Let's see if the square root transformation fixes things. And in our case, yes, it does. It makes that Levine's is now not significant. And so we get that green light here to use that transformation instead. So a couple of questions that came through. Thanks for those that are replying and helping cover them for me. I appreciate that. Yeah, to reiterate some of these AL and AS that I'm throwing around, those are transformations. So they are codes here in the ARM action codes. If I go down to like the AL, basically this is going to apply the logarithm transformation, or the AS does the square root transformation on all of the data points. So we're going to treat them all fairly, but it's called an automatic transformation because we're not going to change the data that's in this column. We're going to leave the data alone, and only when we go into the analysis, when ARM runs the AOV analysis, then behind the scenes, it will apply that transformation to each of these data points and then perform the AOV analysis on that transformed data. So, it's pretty nice that we're not changing anything that was entered. We're leaving that totally alone, but we're giving some instructions for later on for ARM when it's doing the analysis for what it should do as part of that analysis. So that's those codes that we're kind of throwing around here, really just deciding what action, what instruction should we give ARM for that next step when we do the AOV analysis. So in our case now, we've told ARM to look at the rating type, so it's count data, and it comes back to say, all right, count data, the square root transformation fits with count data, and it also stabilizes our variance. So that would be the best selection for us. So I'm going to double click on this row, and you'll see that the action codes is updated here for this column. But nothing else has changed. So we've left the data alone, and we will see that change just when we do the analysis. It'll be adjusting our analysis for us. So some good questions there to clarify what we're doing here. All right. So that's really the nuts and bolts of what our diagnostics panel here is doing. We're running statistical tests to test for those assumptions. Then based on those results, we need to decide what should we do. And ARM has a nice recommendations engine to decide and help make recommendations for us based on those 4 tests. A couple other tools that we see here on the screen. So what we have here is a graphing tool, not so much graphing the data, but instead it will display some diagnostic graphs. I'm going to change this layout to 2 by 2. And so this is going to show us some diagnostic graphs for the AS code that I have selected here. So you can see if I change my row, that text will change as to which graph we get displayed for. So when I press the show button, ARM is going to generate some graphs for me. I'm going to try to zoom in a little bit so it's not too small, hopefully. So these are some diagnostic graphs really to dive a little deeper into the analysis. So, depending on your level of expertise, we could just go with ARM's recommendation and move on. Or if we want to, take a closer look at the data, this is an option to go even farther. So what we have is really 2 columns of information with this AS graphing here. I have on the left the AOV residuals, which is really just the raw data without any transformation. And again, we are looking at the residuals of the raw data. That's what we're going to base our analysis, our decision making on. And so we have a box whisker, which, as we mentioned before, is a real nice way to visualize the variance. Just looking at the height of each of these boxes gives you that look at the variance, and what you're hoping for is consistent height. We really don't care if they're all really tall or all really small. It doesn't matter to the AOV analysis as much as the consistency of those heights. And in this case, you can see treatment 1 has a lot of variability, treatment 3 a little, but the rest of these are fairly small. And that is reflected in our p-value, where we had that significance in the Levines. So that was kind of that original issue that we saw, and it's failing that test for homogeneity variance. So on the right is that AS. So we had kind of our proposed action to take. So now we can kind of compare. Here we have a problem. The proposed solution is to apply the square root transformation. Let's look to see what that does for us. And so now we can see the box whisker, after applying that transformation, gives us more consistency. And we can also see in our test, the Levine value, p-value is now not significant. So we feel much better about the homogeneity of variance if we apply that transformation. And there's a few other graphs, one really kind of corresponding to each of our statistical tests that we're running. Oops, page 1 here. Still, we have a normal QQ plot. And that really, the goal is to look at the general normality if your distribution is bell-shaped or not. And so for the residuals without any transformation, we had no problem. I like looking at that p-value, tells us there really is no problem. I'll admit I'm not an expert at reading a normal QQ plot, but the fact that these are all fitting in nicely here, and there's no real extreme values outside the 2 and 3 standard deviation curves tells us that we're doing good, that there's a bell shape there, and really the same thing with the AS. So we didn't break anything, essentially, to know that we can still trust the normality even if we apply that square root transformation. Going on to page 2, there's a spread location graph. Gives us a sense of the skewness. We can see here that, in the end, we don't break the skewness. It does look like it gets maybe a little worse, but as long as we're still not significant, I think we still feel pretty good about using that AS code. And then the last one is looking at kurtosis. And so that's a histogram of the values, again, the raw residuals, and then if we do the square root, and both of them look great in that regards. So again, these graphs here, we brought those up either from the recommendations table, or that you can also display them up here on the diagnostics, just whichever column that you're that you have selected up here will be the graphs that you generate. And if we were in a, let me go to column 3, before we actually had a transformation applied. And so if you have IID selected, just real quickly, I'm going to show those graphs. The difference there is that on the left, you have the raw data, and on the right, you have the residuals. So since there is no transformation applied, we're just have the raw data and then the residuals on the right, which again, the ones on the residuals is really where we're trying to base our decision making for testing the assumptions of AOV here. So that's kind of a deeper dive. I won't spend more time on that since it is a little more advanced. Certainly really great visualization for those that want to go deeper into visualizing what we're recommending essentially. So that in general is the workflow. You know, it's kind of wordy as we're explaining it. So sometimes I feel like it seems somewhat complicated, but it's actually pretty easy. So, you know, if I click into column 3, typically for me, if I was reviewing data, my eyes jump right to the recommendations table. And so I've got IID in all 4 of them. Awesome, fast and easy. There is nothing we have to look at. I'll just click on that first row and get an IID. And then I can move to the next column. And I can either click into column 4, or there's a button down here that says next. That'll take us right to column 4. My eyes jump immediately to recommendations again, and I do see AS. So then I slow down a little bit, say, okay, there's something here. Let's double check. Yep, sure, the Levine's is red here. So we need to consider what we need to do. Check our basis out. We still have the same type of assessment as last time. So ARM knows it's count data. So I feel pretty good about this recommendation. And there is no other issue besides Levine's. So kind of the same thing we did in column 2. I feel pretty good about selecting that AS and being able to move on. A question here about the recommendations or the basis, which criteria have to be followed to select an option. So by default, it starts with assessment values. And like I said, that really is just looking at the data points, which of the the transformations will work. But you can choose any of these other ones, and to kind of show the behind the scenes of how does ARM know if it can take any action on that or not. When you're selecting, for example, a rating type, the important thing is to pick from the list. If you hand typed a rating type that's not in ARM's list, ARM won't be able to take an action on it. It's not going to know what it is if it's not in the list. So that's one important thing to point out. But if you're picking it from the list, you may have noticed that some time ago there was a new column added called family. And that's actually kind of where the brains of this recommendations is hooked up to. So here we have that count of disease, and that family is really where ARM knows, oh, this is count data. So if we scroll through here, there's a proportion. So if you're doing a percent control, that's how ARM knows that's a proportion, which would be between 0 and 100 versus percent could be over 100 if just depending on how it's calculated. So there's a lot of these that don't have anything. So if you're just content of sodium or something, there's no kind of rhyme or reason or natural fit to one of the transformations. So that's empty, no harm, no foul there. But that's really where that basis is coming from. Is some of these assessments, ARM will recognize that, and that's how that basis is connected to it. Just the same in the rating unit. So there's a family there as well. And so that's how ARM knows and hooks up to that. criteria. And so the choice is kind of yours, and that's why we have this box right here, is so that you can make that decision. You know this assessment. What is this assessment? So you can make that choice easier than ARM just guessing, especially between rating type and rating unit. Just from a computer probably can't really tell which one is definitely the one to pick. But of course, the researcher knows which is most representative. What's going to tell ARM the most? Is it count data or is it a number? So that's kind of leave it up to the researcher to feed that information to ARM, and then it can give you that recommendation. Great question. So here, column 4, we chose that AS. We'll just keep going here to kind of show it doesn't have to be overly complicated. Here in column 5, I can see IID all the way down. So we feel great to just double select IID, or maybe I'll click this box up here. Again, either way works. And I can just cruise through. Yep, all of them are IID. So I can just keep moving to the next column. It's definitely going to depend on your research type, of course, what types of assessments you're making. They might all have, typically if you're doing a lot of counts or whatever, you might end up with a lot of that, or you might end up with a lot of IIDs because they all are bell-shaped without any troubles with the assumptions of AOV. It's really just going to come down to maybe the type of research. You can see it can be pretty quick. And I know I have a problem column coming up next here one of these times. This one is still good. You'll notice that there is an action code here in column 11 already. There is an AUD PC calculation. So this is a transform data column, but that is just fine. Certainly we can include that in our basis. This would be one example where then ARM can at least know that this is calculations. But in our case, we have nothing to worry about, so we can move on. And you'll notice if I double click that, it leaves the action codes that were there in place, and it just appends that IID. And the nice thing about the action codes is it can be just a list of multiple things. All right, so column 12, I knew it was coming. We had one problem one here. Maybe before I dive into that, we had one request about a disease rating. And I'm not sure if in this particular trial I have a disease rating, but in general, just to show, again, it would really just come down to the way you filled in the column. If I filter for disease here, and if you have a typical rating type you typically are using for that disease rating, I don't know if it'd be the damage from a disease, or what the rating type would be. Again, it's all going to come down to whether there's a family or not, whether that basis is really going to change. But it really that would that be perhaps a percent, maybe yeah, pest severity, thanks. That'd be a good example. Searching for a disease wasn't a very good filter. PESS, pest severity. So then a unit there, that would be good for that. Would you typically do that as a 1 to 5 type of scale, or would that be like a percentage? Kind of just depends. Perhaps if you're doing a scale rating, that one definitely has a family to it. That is definitely a unique type of assessment. Most likely, it might be a little hard to get a bell shape out of that one, for sure. Of course, I don't have any real data. Oh, it's not liking my calculation now. I don't know if this is instructive or not, perhaps, since it's not real data, and obviously I'm just making it up. It might not be super informative. but we'll just put stuff in. But we kind of mentioned this a little bit in the first day when we were talking about the data corrections and what they're good for. That a lot of times the type of assessment you're making kind of lends itself to a certain distribution. And so, you know, pest, if you're dealing with something like bugs that might be rare, and you'll have a lot of zeros, and then there'll be one spot where there's, you know, a lot of infestation, but otherwise it's fairly rare, then you'll never be a bell shape, of course, because you're going to have so many zeros and then a few spatterings of that infestation. It, you know, definitely lends itself to you're almost never gonna get the Shapiro-Wilks to pass, because it's not bell-shaped at all. And so that's kind of the nice part about this basis, is then to have ARM know that this is the type of assessment I have. In this case, it would be that rating unit 0 to 5. So it knows to kind of expect that you might have lots of zeros and not much of anything else. So I think that's the Poisson distribution. I could be incorrect. I'd have to check my notes, but that'll then give that good recommendation of, well, we typically use this for that type of data, and that'll hopefully fix it. So you really have 2 steps to that recommendation. What type of assessment is this? That'll kind of narrow down which data correction makes the most sense. And then we look, of course, at the actual test itself with that transformation to decide if that actually makes sense. Of course, if we still don't pass the assumption of AOV, then, you know, there's no point in recommending that transformation. And that'll actually lead us right to the next example that I want to show of what happens if one of those data correction transformations isn't the answer. None of them fix the problem. What do we do then? So hopefully that kind of helped with the disease rating. I don't think it was probably the most realistic example there, but I do have actually that very same situation here in this lodging data. Most of this is zeros, you can see, except for a few cases where we do have the presence of something. So here zeros for many things. We can imagine that the distribution is not going to succeed at being normal. And sure enough, if we look at right now, it knows it's a percent. So we have the automatic, or the arcsine square root percent as our proposed data transformation. However, we still don't fix the issue. We still can't make it bell-shaped. So the Shapiro-Wilks, the skewness, and the kurtosis are all failing. So we mentioned this in the slides. If all of those fail, we don't have an option. Really, we say, all right, well, we don't have the ability to fit into those assumptions of ANOVA. So let's just not use ANOVA. Is really the next option. And so that here we can see in the recommendations, the code here is AR, which would be, in a sense, the automatic rank transformation. But really what that triggers is our non-parametric statistics. So if I double click here to add AR, the nice thing is this slides right into the rest of our workflow. We're giving instructions for ARM that when we do the analysis, I want to apply that automatic rank transformation. But what that really is instead of doing AOV analysis for this column 12, we're actually going to do non-parametric statistics. I wanted to show this list just to show that depending on which experimental design you have, ARM will choose the appropriate one, but there's a Kruskal-Wallis, a Friedman's, and an aligned rank Kruskal-Wallis analysis. Those are the 3 different types of non-parametric statistics. kind of the system of how to rank. How do we want to rank the values? And so when I say by rank, really look at just putting all those values in a row from lowest to highest or highest to lowest. Probably depends on which one it is, how it's done, but either way, then we assign a rank: first, second, third, fourth, and so on. And then we can use those values to analyze the results instead of the individual values. So kind of a whole different statistical system. We won't get too much deeper than that into it, but now you're not dealing with means and standard deviations, but it's more about the median. And it's a little less powerful from just in the statistics realm, and that's why AOV is usually the first choice. There's just more statistical power in that AOV analysis, so that's why we always start with it. But here in these cases, like this assessment, certainly non-parametric is better than nothing. For sure, it's definitely better than getting something we can't trust in the AOV. And that's really why we spend so much time and care about these tests for the assumptions of AOV. Is if we just ignore them and just run all the data through AOV without checking this, then we really can't trust those results. When we get our letters and we see what is different, we're basing all those decisions on some assumptions that may or may not be met. And so we really can't believe what we're seeing then in that report if we don't spend some time in this data review process to do the right thing and make sure the data is going to be set up for that analysis. So again, this AR action code is really the way to trigger the alternative to AOV, which is the non-parametric statistics. And so just to note, all of our examples before, we really had a problem with Levene's, and we just happened to have the normality was all fine. But in this case, you can see that we have two tests that are failing. And so depending on where your data lands, you might have not necessarily conflicting recommendations, but you might have more than one recommendation for different transformations to apply. And so really, our statistician who designed this tool had put these in order of importance, at least within this realm of what assumptions for AOV are maybe the most impactful, if you will, for trusting those results. So, for example, here we have Levene's. Everything is fine in Levene's, but that doesn't mean we should ignore the rest of them. But as you work your way down, it's maybe just a little less impactful. So, for example, if the recommendation for kurtosis was the automatic arc sign, so we kind of had a conflict here. One tells us AR, one tells us AA. The other two don't care because it's IID. It's like, well, what should I do? You would really just kind of lean towards what's the first one in this table, working my way from top to bottom. What's the first one? That one would be the biggest one to deal with, if that makes sense. I'm not sure if I have. We'll keep moving to the next few columns. That's got AR. I don't know if I have one that's quite that complicated. No, the rest are fairly straightforward. So that's really just, we've kind of numbered those rows to just give that guidance of, okay, if this looks kind of like a mess, I've got a whole bunch of different recommendations everywhere. Just work top to bottom and handle whichever one does the best job to deal with Levene's and Shapiro-Wilks, and kind of goes down. If they're all a mess, it might be wise to consult a statistician. That's kind of ARM's goal, is to do the 95% of cases, try to do the best at the basics, and then sometimes if things are really unusual, then it's good to maybe export this out and have a professional, if you will, take a look at it. Great question. Does the data have to match all, have to pass all 4 tests, or is Levene's enough? As typical with statistics, it's usually not just black or white. I don't have just a yes or no because it's statistics, of course. If I understand Peter correctly, I think he would say that if you look down and Levene's is fine, Shapiro-Wilkes is fine, but maybe kurtosis is just a little bit significant, you could debate whether it's worth putting on a transformation. So, if the first 3 were IID and kurtosis was just barely like a 0.04, just barely significant, is it really worth going through transforming the data when there's just a little bit of kurtosis? I think there's room for some executive decision, if you will. I'm sure there's a statistical term for for kind of going with your gut on that. But as I understand, there's a reason Levene's is first. If there's a problem with Levene's, if there's a problem with that homogeneity variance, you really want to deal with it. Shapiro-Wilkes is usually fairly important, but like I said, as it goes down, you get a little wiggle room. So yeah, as it is with statistics, and there's never a simple answer. But I would say just personally, without a without a deep statistical background, so take this with a grain of salt, that definitely deal with Levene's. I feel like Shapiro-Wilkes, it's there. It's not too hard to add that, unless the recommendation, let's say the Shapiro-Wilkes recommended the ARC sign because it fixed it for Shapiro, but then it caused problems elsewhere. If you just don't have a good option, then maybe you can tell yourself it's fine to leave it. But you always also have that non-parametric statistics as well. So I think if it were me and I couldn't quite make a very simple decision based on the mess of recommendations here, maybe it's easier just to turn on that rank transform, just do the AR and say, well, I won't even deal with it since it's hard to make sense of what I should do in this AOV realm. Well, let's just do the non-parametric statistics and go that route. Again, that's a very non-trained, non-statistical person giving advice. So take that with the as far as you're willing to go with that. But hopefully this demonstration in this particular trial shows that it's hopefully pretty rare that it ends up being that messy for you. Hopefully there's a lot of IIDs, or there's a nice simple pattern that I'm dealing with. In our case, it was count data, and they typically all kind of match the same flow, where we typically had this problem with homogeneity variance, and that was the only thing we had to fix. I would be optimistic that that's usually the case. But hopefully this tool can give some baseline, I guess, if you will, for if it does get more complicated. So great questions. Sorry I have long, complicated answers for all of them, but I guess that's what we get for doing a statistics session. So I guess couple of other little components to this tool here that don't need tons of time to spend on. Let me move. I was clicking to column 3 since we haven't mucked that one up too bad. Would be spatial models. So we mentioned that in the list of our toolbox, we've used data corrections. We've done the non-parametric statistics. The third option that we had listed was spatial models. And in week 1, we did mention that's kind of a rarity. really what that is doing is throwing out your blocking structure and kind of starting from scratch. So it isn't something that I would put on your regular radar of what I should be turning on or off, what should I be looking at. But in examples where where things just didn't work as expected, it's a tool for one of those kind of extreme situations. And definitely, if you don't feel very statistically inclined, I would almost say I'll never turn it on. And if I need somebody, I'll just, if it gets to that point where I might need that, I'm going to ring my statistician. I'm going to get someone else involved. That's at least that's how I feel if I was doing the research, because I don't understand the underlying statistics much on these spatial models. But if you want to look into those and to utilize those, there's just a box up here at the top of the diagnostics to include spatial models. And really what that does is just adds a few more options, actually quite a few number of options here to the list of possible things that we can use. So these are all, actually, I'll just turn this one on for the moment. These are all also action codes. If I bring them up from the list, you'll see that they're in the spatial models. So we have a linear spatial trend, a quadratic, cubic. So those are different trend analysis based on the data that you have. Then there's also a nearest neighbor and a few different combinations of those. For just looking at spatial trends, again, we're throwing out any blocking that you did, whether it's a RCB design or however you had it laid out. We're just totally ignoring it, and let's start from scratch and see if there's some sort of trend that we can look at spatially using your trial map and the sizing of your plots to figure something out, essentially. So that adds more recommendations. Here in this column, we actually have the quadratic spatial trend is actually an option to stabilize the variance. Like I said, that's about as far as I can go statistically. I don't have a great grasp on some of the nuances to the spatial, but there are two more things in the recommendations table. And a couple of statistics down here, AIC and BIC. As I understand, those are really trying to give a number to how well does that particular model fit with the data. And so in this case, it's telling us these two also improve that AIC and the BIC compared to what we have currently in the design. And yeah, the nuances for what AIC is telling you and BIC, a little over my head, I'll admit, but that's really some of the tools that you get with the spatial models. And there's also, when you show the graphs, you get the same ones that we had before, and then there's also a couple more. So there's a heat map basically of the residual map. And you're looking for, I think, totally random is what you're hoping to see there. And then there's also a semi-variogram. So just more diagnostics as well, looking at the spatial aspect of the data. Again, just turn that on or off with the diagnostics there at the top. Let me turn that LST off as well. Finally, last thing on this panel, down at the bottom, right next to that next and previous, there is a Save To button. So you can take this analysis, all the work kind of done behind the scenes here is all done in R. So ARM uses R in a lot of the analysis when we're doing the reporting, as well as totally entirely here in the diagnostics, we're using R in the background. And so you can actually save the script, the R script that's run in order to give us all this information you can actually save that to a file. So you could open it up in R Studio or the console version of R. And if you, do whatever you like with it, you could take it apart and run your own sequence, or if you just want, play around with it and see what we are doing behind the scenes, there's those options there. And we also have an option to save to SAS. So basically the equivalent commands that you would use in R, we kind of translate them into the SAS world and have that script of what we ran here, but that to be run in SAS. And again, that can be whether it's just for your information, you just kind of want to take a peek under the hood to see what we're doing, or if you want to take that and run with it and do whatever you might want with it, that's totally fair game. So that's available at the bottom here. Again, specific to kind of what we're doing here, running the statistical tests and things like that. Those graphs, I think, are also generated in R, and I believe that would be included in that script there that you can generate. And then real quick, just want to, we mentioned it earlier that this tool is relatively new, 2-3 years. I think we've had it in ARM. So before that, we had a whole different set of instructions for reviewing data. And a lot of it was tied to the reporting. So I just want to show, in case you still have that on from earlier, if you've used ARM for a number of years, you probably would recognize that prompting. But in the AOV means table options, here on the general summary tab, it's towards the bottom, there's an option to apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. Besides being probably one of the longer options we've got, this was the old way to review data. And it would just, it was very smooth. It was very quick, I guess I could say, that when you generate the report, ARM would just give you a list of all of the things it found. I would say there's really 2 reasons to turn this off. Number one, that engine was based on kind of the older, more classic statistics, where we looked at the raw data and ran those tests. Bartlett, I think it still would use Levine's, and skewness and kurtosis were the 3 it would run, but it's not using the residuals. That's kind of a more modern technique that's found in column diagnostics. This tool itself has stayed the same. That engine there is still looking at the raw data and running those tests there. So, kind of just bring yourself up to a more modern statistical approach by turning this off. And then the other part is some of the recommendations here weren't the best, because it would recommend excluding a particular treatment or excluding the check, partially because we didn't have non-parametric statistics back then, so you really didn't have other options. But now that we do, I think that's a lot better recommendation. So I think you get better recommendations by turning this off and using the diagnostics. And also just from a statistical, holistic, you've got a more modern approach by using the diagnostics. All right, so we've hit our time. I can stick around for a couple questions. I see one right there, but I don't want to hold anyone hostage. So I want to say thanks to everyone who joined. I'll definitely keep the door open here for some questions as well, but don't want to hold anyone to it. So thanks, and maybe we'll see you next week. And definitely send any questions. If you're typing them up here, I can still spend a couple minutes on them. And the first one here was an independent archive is generated when saving to R. So yeah, let me just click on that button to show that when you say save to R, or any of these options really, then when you press that button, it will prompt to create a file. And here I could just drop it on my desktop. It'll save that script as its own file here. And I'll, like I said, I'll save that to my desktop. And then you could open up the R program or your R Studio and then load that script. So there now it's living on my desktop. So it is separate. So then you close ARM, you can move on to something else, and that's just fine because there it is on on my desktop here. I don't think I have. Well, I do have R. Let's see if it'll open up there. I'll admit I don't spend tons of time in R. Nope, I think there must be a different way to load that script. But you get the idea. Yep, it is saved to its own file, so that way it exists outside of ARM. Great question. Any other questions? I appreciate the ones during the session. That's always great to have that dialogue back and forth, and definitely make sure that we're covering the topics that are helpful too. So. All right, well, thanks everybody.